Okay, let's start. All right. Any questions so far? Are you guys okay? It's getting a little more integrated understanding now. So not just fact by fact understanding. So I also recommend you to look back the previous materials when we talked about light or CO2 or temperature. That way you can re-establish your foundation, because you need foundation to talk about integrated stuff. So we are now going into the system understanding. So this week we are talking about greenhouse systems. And the contents I'm talking about this week, so the two lecture lengths of contents, basically the essence of what you learned or you will learn or you may be learning in the future in greenhouse course like Dr. Jean Giacomelli teaches, greenhouse design and systems, greenhouse systems and design. So, but my talk is always in the standpoint of crop growth enhancement, how we can improve the climate so that improve the crop performance. So that's probably the difference between his and mine. I have, oops. So greenhouse environment number 1, number 2 will be on Wednesday. Some engineering stuff. But this is the first one. You are going to enhance the system understanding of the crop production in controlled environment. All right, so there are 2 references actually. The first one is written in the handout. Second one is missing, but I have that in the D2L. Second one is optional and advanced reading for graduate students, most likely, and then undergraduate students who are very interested in this topic. But the first one is only a few pages. It's a extension article, so it's a summarizing, greenhouse covering materials or glazing, how glazing works in the greenhouse climate. But second one is many pages, 30, 40 pages, but it's a review, technology review, paper review, so that's a good one. So that's why I decided to include. So greenhouse environment, we start light environment in the greenhouse. So the light in the greenhouse, usually the solar radiation, right? And then we learned that short wave radiation is the short solar radiation, and then the radiation range is 300 to 3,000, and then within that 400 to 700 is the PAR, photosynthetically active radiation. So the role of solar radiation in a greenhouse, not just for photosynthesis. We in Arizona don't appreciate much in terms of thermal effect of solar radiation, but greenhouse is originally developed as a season extension so that farmers and growers can start early by having a protection and then having higher temperature inside the greenhouse compared to the outside. So that was the original purpose of greenhouse. But anyway, so the solar radiation in a greenhouse is a thermal energy source, and increasing temperature of the plants and then also soil. Anything absorbing solar radiation increase the temperature, right? And then plants have evapotranspiration, so that sort of balancing out the temperature. And then solar radiation is a big component of the energy balance, so it's almost like a driving force of evapotranspiration. When you have a huge solar radiation, you will have a large, evapotranspiration rate. In terms of plant response, we run that photosynthesis, and specific wavelengths 400 to 700. Photomorphogenesis, red and far red, and then also other wavelengths such as blue wavelengths involved in photomorphogenesis, and pigment synthesis like UV light. So very important, you know. So the light intensity and quality, how different inside the greenhouse compared to the outside the greenhouse is the goal. In understanding that is the goal of today's lecture. Changing day by day, minute by minute. So it's not consistent. Okay, so that's the sort of challenge of greenhouse light environment. But some of the key to understand the light environment in greenhouse, glazing or the covering material not transmitting the light 100%, always either reflect and or absorb, and then usually both happening, reflectance and transmittance and absorptance. So the three components equal to the incident light. So the reflected light plus, so that's the equation. Reflected light or radiation, absorbed radiation, transmitted radiation equal to the incident radiation, right? And then usually you want to select the glazing having high percentage of transmission, right? Otherwise, you can't increase temperature to warm up in terms of, you know, wintertime production, or you can't get enough power, photosynthetically active radiation in a greenhouse. So you got to select the good glazing having high transmission. Right, and then that transmitted light is the incident light over your plant canopy, okay? So now we have two incident lights. So the incident light going into the greenhouse, incident light going into the canopy. Okay, so the incident light going into the canopy is the transmitted light through the glazing. Okay, all right. So it's basically a double, you know, absorption system. And then out of that, you know, much of the light is supposed to be absorbed by the plants. Some of them reflected, some of them transmitted through the canopy. Okay, so that's the greenhouse. So again, this equation also meet the shortwave radiation over the canopy equals three components, and then you want to have this component, you know, absorbed one maximum in this case, right? Okay, so this number is really helpful. Understanding how much energy coming from the light is actually utilized for plant, you know, structure or body, biomass. So the table is showing the percentage starting from the incident solar radiation over the greenhouse. So the incoming solar radiation at any point, 100%. And then how much percentage is in the greenhouse, how much percentage is absorbed, blah, 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 blah. And then at the end, it's very low. So let's go look at each step. So the this one is the ratio, 0.5, is the proportion of power in the shortwave radiation. Shortwave radiation is again 300 to 3,000, right? So the power is a photosynthetic active radiation, which is about 50%. So we can't really change this, right? 50% or whatever the number, we really cannot alter this because it's a natural light. So let's take 50%, which is close to what reported. So now available energy is only 50% of the original energy, available energy for photosynthesis, okay? Then out of that, some is going to be inside the greenhouse in transmission. And then some of them reflected, some of them are absorbed by the material or the, you know, structural component. So this is a ratio or percentage of the transmission of incoming light through the glazing. So let's say average per day, 70% is transmitted in the greenhouse, which is quite high actually in terms of number. Okay, if you measure the light transmission, you will see the value later. In the lab, you get 90% transmission, you get 95% transmission. But if you look at the daily average, sun is moving from east to west, and then structural angle, everything affect. So the average transmission per day is usually 60% to 70%. So 70 is relatively high. So I assume in here 70% of the light going in the greenhouse. So that means it's already 50%, right? Because PAR, and 50% of 70% of the 50% is 35%. Okay, and then the next step is finding out the percentage of that incoming PAR absorbed by the canopy. Okay, so the amount of light is coming now in the greenhouse, and then maybe you have a walkway, maybe you have not fully developed canopy, so that not all the PAR, photosynthetic active radiation, is used by the plants or received by the plants. Therefore, I have relatively low number. You can argue, okay, I'm going to use, for example, deep flow hydroponics. My greenhouse is entirely covered with plants. In that case, I can use much higher, utilization factor. But let's say a conservative number in this example, 0.5. So 0.35 times 0.5. Okay, only half of that is actually absorbed by the canopy, so 0.175. So 17.5% of the original solar radiation is now absorbed finally by the plants. And then plant photosynthesis, if you know, it's very energy inefficient. Absorbed energy, and only 10% or so is going to be actually fixed and then converted into the chemical energy. All right, so that's the gross photosynthesis efficiency, energy utilization efficiency. And then I use 14.3%, so 0.143. Now I multiply with that, and then the energy portion finally, fixed by gross photosynthesis of the plants is only 2.5% of the original light. And then plants need to do respiration, so fix the energy into the carbohydrate in a chemical energy format. However, they need to consume that energy to maintain the metabolisms. That is the respiration. So the respiration loss is 40%. And actually, respiration loss is in this case 60%. So the only 40% retained in the plants. You can argue that, let's lower that. But anyway, so in this case, I have 0.01%. No, 0.01 to relative to 1, so it's just 1% of the original solar radiation. And then if you're growing lettuce, your energy conversion from solar radiation to the crop is 1%. But if you are growing fruiting vegetable, those crop having a harvest index not 100%. And in that case, you need to consider that. And harvest index 50%, which is also a conservative number. And then finally, this table is showing only 0.5% of the initial energy is now in the product you are obtaining in the greenhouse production. So all these numbers in red is something you can, improve. Transmission of the greenhouse can be improved. And absorption by canopy can be improved by designing the greenhouse, eliminating wasteful, space. Planting density, right? That also can be adjusted to maximize the space use, and then therefore the light use. And photosynthesis, you can enhance that, photosynthesis efficiency, maybe temperature control, CO2 enrichment, all that, potential strategies to enhance the photosynthesis can be used. Respiration, maybe lowering temperature, all that strategies you can include. But you see that how low those numbers are. Okay? All right. And yet the plant production is always linear, as long as dense canopy is our concern. And then this is I might have shown this in earlier lecture. This is a commercial greenhouse tomato production yield curve, and so there's a lag time because there's a vegetative growth period before the harvest, and the harvest starts, so that this is a cumulative yield of tomato fruits over the cumulative energy, solar radiation, which is 300 to 3,000 nanometers. So it's not PAR, but PAR and solar radiation is very much correlated, right? When PAR is higher, that means solar radiation is higher too. So when you see the correlation with yield and PAR, you should be able to see like this yield and solar radiation. But this is a sort of rough conversion of, by the way, this is a cumulative energy. So every day, you get some megajoule per square meter solar energy. Okay, and then if there are, for example, 10 megajoule per square meter over the 10-day period at that same solar energy coming from the sun, and then your solar radiation is 10 times 10, so the 100 megajoule. And then this is a gigajoule, so it's much longer period. So 1 gigajoule is probably, I would say, 3 months or so. I would say 20 moles per square meter, 100. Yeah, so about 3 months or so, depending on the season. But you can see that linearity. And 1 gigajoule per square meter cumulative solar radiation is about 2,000 moles per square meter. So if you have this kind of graph, you can actually see many things. By the way, 4 or 5 different lines are different crops, different compartments, maybe different varieties, but started almost at the same time. And then the linearity or the slope is about the same, and that is suggesting about 10 grams of fruit you can expect per additional 1 mole of light, solar light, actually PAR moles, because I converted from 1 gigajoule. So if you just kind of look at how many gigajoule per how many kilogram, and then you get that kind of information. So this is actually exactly following. Light is very important. You don't want to lose the light in the greenhouse. 1% reduction or increase in yield is coming from, or the other way. 1% reduction in the solar radiation or PAR is going to result in 1% reduction in the yield. So it's high correlation showing that. Okay? All right, so greenhouse. This is some of the pictures of high wire glass greenhouse, Dutch vendor greenhouse. I don't know if you can see in your slide screen. So right-hand side is clean glass. Left-hand side is coated, so that the greenhouse coated with some whitewash to reduce the radiation. Sometimes you need to reduce the radiation, not just for, actually not for photosynthesis. You want to maximize photosynthesis, so you want to go as much as possible to meet the 1% rule. But greenhouse, because solar radiation have much heat, 50% heat, unusable energy for photosynthesis, and much of the PAR is basically not going to be fixed in a chemical form, right? So that means if 10% is fixed, 90% is going to be somehow escaped as heat. So basically, solar radiation coming in is entirely heat. So if too much radiation outside, you really need to reduce. Otherwise, you can't really maintain the temperature. So in that case, you use materials like that or internal movable shade screen or outside, either way. But that is really important greenhouse management technique. Otherwise, plants get stressed, high temperature stress, high radiation stress, and then your yield is not going to follow the previous straight line. Okay. The picture underneath in here is cleaning machine. So light transmission is very important. 1% reduction is not going to be accepted. Therefore, high-end greenhouse is equipped with this machine, automatically clean the glass surface every week or so to remove the dust, remove whatever the materials or particles, reducing the transmission. So, yes?
How would you know, or what device would you use to determine how much is actually being used for energy as opposed to heat transmission? What, in 2 slides prior to
Yeah.
your hypothesis and available energy, then how do you know that?
How do I know that?
Yeah, what did you?
This one? This part? The number?
Any of them.
Well, so that's for literature base and then also measurement base. So those numbers, transmissivity is pretty much reported, greenhouse engineering type of papers. And then we have done that in our greenhouse too. Our greenhouse is, the compartments are much lower, 50%.
You just use the
Sensor.
white.
Yeah. So we have sensor sitting in the greenhouse, and then to understand that per day average, you have to leave the sensor multiple days and integrate the DLI in that sensor. Then another sensor outside without any shade around, then integrate the same way, the daily light integral. Then just compare 2 values, and usually 60-70% if the greenhouse is well designed. 50% like those college compartment gutter connected shady greenhouse. So yeah, so that's how you find by measurement. And then also there are reported values out there too. And then one of them is the extension article you will be reading. It showed some percentage. Yeah, so there's a measurement or the difference. Is that, that's it? Okay. All right. So this is a shade cloth. This is a greenhouse which is used relatively low light, crop. Like this is what spatifilum. That's an ornamental crop, and then they like relatively shady environment, humid and shady environment. So they usually have screen like that, and then they also, because they are shade crop, therefore they put more plants up there without worrying about too much shade on the crop. In tomato greenhouse, you don't do that because anything above overhead head space is going to be shade creating object, which should be avoided in highlight crop like tomato, cucumber, those ones. Another question? No? Okay. Yeah. All right. So factors affecting greenhouse light environment. There are many factors to consider. So the first one I put is the incident light quality, but it's not spectral quality. It's a more like directions of beams, direct light and diffuse light. And then I'll explain a little bit what it is. And of course, glazing material, what kind of glazing? Is it glass? Is it, different materials? And then its optical properties affect the greenhouse light environment. and how much structural members, the structural components are used, and a greenhouse geometry, size and height and everything. And orientation, which is facing east, facing north, that is definitely affecting greenhouse light environment, which is probably more intensively taught in greenhouse engineering. But I'm going to show you some examples to enhance your understanding. And then location of greenhouse and time of the day, time of the year, because the location of the sun relative to the greenhouse. All right, so diffuse and direct light. So sunlight, you're outside and receiving sunlight, and what you see as a strong beam is basically direct light, which is creating dark shadow. Okay, you have also another component in the sunlight, which is called diffuse light. So the diffuse light is basically, the sunlight is basically everywhere, right, from the sun. And then the one deflected by the particles somewhere in the sky, okay, is the diffuse light. So the cloudy day is basically 100% diffuse light. And then in that case, there is no shadow because directions of the beam is everywhere. It's not directly from the sun. It's bouncing somewhere in the atmosphere. So it could be behind me, could be in front of me, could be from the side. So it's in all direction. That's the diffuse. And then depending on the locations, diffuse light percentage is high or low. Arizona is very low. You can imagine. When you take the picture of Arizona sunny sky, it's so blue, right? When you go to California or Florida, sunny day, you go out, take the picture, it's kind of whitish, low intensity blue color. And why? Because of diffuse light. So we have much less diffuse light in Arizona because the moisture content affects the diffuse percentage. So the incident light is called global light. So global light includes diffuse light and direct light. And diffuse light is usually lower percentage unless it is a cloudy day. And then it is very important component because, for example, in this model, the tree facing the sun is pretty much receiving direct light and then diffuse light, and then behind that is only diffuse light. So the diffuse light is supporting the shaded part of the plants, okay? So diffuse light can go deeper in the canopy or behind the plants. So that's the diffuse light, all right? So that explained in here. So the radiation reaching after being scattered by water vapor or other particles through the atmosphere. And diffuse radiation is very important for crop production as it potentially improves light environment inside the canopy. And then I'm going to talk about this a little bit later when we talk about glazing technology, okay? So this one is showing 3 different weather conditions. Number one is clear sunny day, just to show the relative amount of diffuse light to the global. Global is a total. Global radiation equal direct and diffuse. So in this case, about 25% or so is diffuse light in the midday, and then 75% or so is in this case direct light. Hazy sky, sunny day, it's still we call sunny day because we can see the sun. But depending on the the sky condition, you see that in this case almost all light is in diffuse, and then during the afternoon time, about 50% is the direct light and 50% diffuse. So those are totally depending on the condition of the sky. And this is an overcasting day. Note that the whole radiation level is reduced. It's an overcasting day. And then the available light is all diffused. Okay, diffused light. No direct light in this kind of condition. All right, so I'm going to talk a few examples of greenhouse design. This is what we call lean-to greenhouse. So the greenhouse is attached to the building. You see this in a school, you see this in a university, you see this research center, because it's convenient. And then the idea is using the south-facing building wall, for the greenhouse space. However, the south-facing, therefore, a lot of direct sunlight coming in, but it creates a lot of shadow to the north end because of the diffuse. Diffuse light is completely blocked, because if it is complete greenhouse, the entire greenhouse, right? So that even sun is this side, and then direct light is basically from the south side, but diffuse light is all over, right? So if something is sitting right here, this side is not receiving diffuse light coming from the behind the building. So that is reducing the radiation. This is a commercial greenhouse in China. It's a very typical Chinese greenhouse called solar greenhouse design. Always single, standalone greenhouse, and then facing south. So the orientation is east-west, right? So the east-west, like that. And then this one is the facing south. And then some kind of insulation material, because they use this greenhouse for winter time. So the extension of the season. And then north side is always thick, very thick wall as a heat sink. So the heat is stored during the day in that wall, and then also ground. Then that would warm up inside the temperature many degrees higher than outside. So it's a very low cost, sustainable, low level though production system. But the issue is this side is very, very low light, even though south facing, but because of the shadow created for the diffuse light. And then many of the locations in China, diffuse light percentage is very high. Okay, so that's why pros and cons in this kind of design. And then more recent design, this is vertical growing building, skyscraper. So, designers think plants can grow in a building. And the plants receive sunlight through the glass, so that's why this building is surrounded by entirely, the surface is glass building. But again, if you argue direct and diffuse light, only the time you get that window, particular window facing to the sun, right? That's the time you get direct light. Other than that, it's all diffuse light. And then plus, in this kind of design, your potential surface to receive diffuse light is very much limited, right? It's only one window space, rather than like a Chinese greenhouse. At least you have a top surface, and then only the north surface is blocked. But in this case, it's only one vertical wall which can be used to receive the diffuse light. So basically what I'm saying is this situation is really, really, productivity is limited. You got to combine electric lighting to illuminate internal space if you're using internal space. But sometimes people don't understand that diffuse and direct light situation. And unless it is arid climate, most of the cases you have diffuse light rather than direct light. All right, so talking about glazing, factors affecting transmission of glazing. So what kind of materials definitely affect transmission, and the coating to protect the materials, particularly for plastic materials, affect the transmission, optical characteristic of the glazing. So there are multiple materials used. Glass, which is high-end material, and then the rigid plastic sheets we are using in those greenhouses, small greenhouses right here. We have plastic film covered greenhouse over there. In the teaching greenhouse we went a few times together is covered with acrylic, I think. The side wall is polycarbonate and the top is acrylic. But anyway, I'm sure this one's acrylic. If anyone know, teaching greenhouse, the roof material, all polycarbonate? Okay, so the side and top, okay, the polycarbonate covered. All right, thank you. All right, so those two materials are very typical in terms of rigid plastic sheet. Plastic film in U.S., polyethylene is the very common material. PO and PVC, I don't think we use much in U.S. in terms of film. And this is a sort of percentage. We have more plastic film covered greenhouses compared to glass or rigid material. All right, and then when you decide glazing, there are multiple important factors. Number one, of course, PAR transmission. You want more PAR to enhance the plant growth. How many years this glazing can last? Every 3 years they need to change, or every 10 years, or 25 years. And so that's very important information. Light quality transmitted through the glazing, it looks fine in your eyes, doesn't mean every single important spectrum is coming through the glazing. All right, so that's very important. Total weight, lightweight glazing material reduce the structural requirement so that you can reduce the shade component. Therefore, you may be able to increase the transmission. All right, and then thermal properties, which you learn more Wednesday, but this is also important because glazing is not just, protecting from wind, but it's also to warm up. So how, what is the thermal property of that glazing? Is it transmitting a lot of energy? Or remember the radiation, long wave radiation. We can cover plants with a bed sheet, but not in a PE film because the long wave radiation goes, away. So depending on the materials, it can protect your plants. For example, glass can protect much better than PE, polyethylene, because the transmission of long wave radiation is much less in glass. But anyway, so we talk about that Wednesday. And then, of course, cost. So this one is a very old material and not even English, so I had to translate. But anyway, so this is a perpendicular lab data, but it is a good reference to see different materials used for greenhouses. Transmission percentage over the spectrum starting from 200 nanometers, which doesn't exist in nature. So you want to focus from 300 all the way to higher or longer radiation. But anyway, so I have glass in here. Okay, glass. So every single one, pretty much good transmission between 400 to 700. It's pretty much 90% or 90%. This is a perpendicular lab measurement, okay? Again, if you put that in a greenhouse, in a design, and leave it one day and then measure the average, it's not going to be that high. It's usually 60, 70%. But as you can see that, the big difference is usually in the UV range, right? Big difference between the glazing materials in terms of transmission is UV range. PE itself, as a PE, untreated PE, polyethylene, which is the most commonly used glazing material, transmits UV very highly, okay? However, most of PE is coated or sort of some kind of treatment to protect from UV radiation. Okay, therefore, if you use the glazing, PE film used for glazing, most of the case you don't have that high UV transmission. Okay, so this graph is a little bit confusing, but that's original, I guess, material information. And then another important information to understand greenhouse light transmission is the reflectance relative to the incident angle. So the light beam, right, relative to the perpendicular angle. So if incident angle is 0 degree, that means light beam is coming at perpendicular angle, right? And then in that case, usually you get the highest transmission. And then when your beam angle is getting higher and higher, so that means much lower and lower in terms of, orientation. And then you get less and less transmission because more reflected, okay, coming low, the beam coming low angle, or the high incident angle, which is a little confusing terminology, then you get high chance to get reflected. All right, so that's why this is an incident angle of light, and then it goes after 60 degrees or so. All right. Okay, so that's why in the lab you can measure 90%, 80% transmission, but in the greenhouse, because sun is not always hitting the glazing at perpendicular angle, always have a chance to get reflected. So the average is 60, 70 because of that. Okay? All right. Not too difficult, huh? And then shade is another important, important material, I guess, to understand the greenhouse environment. So greenhouse is not just glazing, right? You have structural components, and that create shadow. And then gutter is the notorious. That is, too much component, too much structures. Therefore, it creates dark shadow. When you have a high, direct light, you can see that dark shadow. If you have all, diffuse light, you don't see that shadow because it's not one direction. It's all directions, so that you don't see that. It's sort of averaging out. But most of the time, we have a direct light, and then there's a clear pattern in that shadow on the floor of the greenhouse, and that shadow is definitely low light spot. And then if shadow is moving, that's fine, because it's only temporary, right? So the average plants can accumulate light. That's why we are talking about DLI rather than just instantaneous light. So if the shadow is moving, that's fine. But if shadow is relatively staying in one location, that's the problem, because that particular location is going to be low yielding location. So growers need to figure out how to manage that situation, or greenhouse needs to be designed so that minimizing shadow in a greenhouse. So this one is just my cartoon. So just showing if sun moves and gutter is located one certain orientation, then shadow moves. Therefore, it's not creating too much issues. That's why greenhouse orientation is very, very important. So this is a gutter-connected multi-bay greenhouse, okay? And then again, those gutter is the big issue in terms of shadow creation, okay? If the sun is this side, all right? If the sun is this side, then gutter shadows relative, it basically travels across the floor. You see that? But if the sun is, for example, this side, all right? If sun is this side, so this means this orientation is maybe the gable ends are facing east, right? In that case, east, right? And then west. And then in that case, sun is here, this side. And then in that case, the gutter shadow is stick to one zone of the greenhouse, no matter where the sun is. all right? And that is the problem. So you will see the huge, low and high, up and down in terms of light intensity. And then engineers can simulate that. You can measure with whole bunch of sensors, but engineers can simulate using a beam tracking or ray tracking method. So that is done intensively in 60s and 70s. We started using Greenhouse. So this is some of the result comparing the light distribution inside the greenhouse of the gutter-connected multi-bay greenhouse. And then this is showing how orientation affects the pattern of the light distribution. So this is, again, multi-bay. Okay, so the multiple of the greenhouse like this, right? And then the top one, top one is east-west orientation. So that means greenhouse bay is east-west orientation. So that way is south, for example. And then greenhouse is gutter connected like this. And then in that case, as I said, there's a huge up and down. So the south end, so this is the south end, right? And then that is in here, the south end. And then this gutter here is creating shadow right here. So this is the cross section of the greenhouse, 4 bays. So this first gutter is creating this big shadow area. Second one is creating the second one. Third one is here. Okay, so it's across the 4 gutter connected greenhouse, south end, all right? If I change the orientation like that, and now gable ends are facing south, so in that case, in this diagram, this is east end or west end, and this is east end, east and west. In that case, it's relatively smooth, averaging out because shadow is moving. Yes, TJ.
I guess my question was, why is what we would call the correct orientation at a lower transmitted level? Because you have some real high spikes.
I know, yeah.
I guess it's like,
Yeah, so TJ always point out, good point. So here, look at that, 80% high percentage, right? But it's a nice uniform, no too much, problematic shadow area, but average is low, 50%, right? And why is that? Because this is north-south orientation. Sun is over there. This is the south end. All right, the sun is always low angle, all right, relative to the roof, whatever the shape is. It's not coming this way. It's always coming this way, so that there is a high chance to reflect it. All right, east-west orientation, usually you have angle roof, right? Angle roof like that. This is a sort of, I don't have a small greenhouse model, so, but usually here, right? So that means there is a high chance to get, very small incident angle. So that's why the transmission is high. So you have pros and cons. Growers need to make the decision. I want to take high priority for the uniformity, or no, because my plants are actually moving in a greenhouse. My plants are DFT, so the floating system, so just traveling through the greenhouse. I don't care the shadow, because plants are sort of averaging out. Then you would be happily select the first one, right? So depends. All right.
for example, this greenhouse, the teaching greenhouse, how is it orientated?
It's north-south oriented. Sort of. It's a little bit 17-degree tilted, but it's sort of north-south. It's not exactly north-south. Yeah, so why? I'm going to get that question because it's quite important. So this one is the seasonal change relative to the orientation of the greenhouse, and also whether it is a single standalone greenhouse or multi-bay. And it's so different. So it's only showing 6 months because it's basically mirror image, right? So this is the longest day, highest radiation time, and this is the shortest day, lowest light intensity time. And then so the single standalone greenhouse, east-west, is always the best option, in terms of average transmission. Single. If you have multi-bay, you have a reduced transmission, east-west, particularly in the winter time. And then those two are north-south orientation. And this is a single bay or the standalone, and this is a multi-bay. But the difference between single bay and multi-bay seems to be similar when it is oriented north-south versus east-west. Again, the shadow is creating huge difference coming from the gutter. So if it is gutter-connected greenhouse, you have a huge reduction of light. That's why you see the big difference in terms of east-west orientation. Okay, so this is the multi-bay east-west, and this is the single standalone east-west. All right, and then that, if you can imagine, that difference, seasonal difference, is getting smaller when you have a lower latitude close to the equator, because the seasonal difference of the sun angle is smaller. So that's why you have a less impact sorry for the super low quality of graph. But if you go north, then you get a huge difference in terms of different orientations of the greenhouse. And this is also another. So this is 5 degrees north, 15, and 25. So again, when this kind of study was done, it was pretty much greenhouse for northern states, and then also northern countries as the users. So that's why a lot of study was done. But now greenhouse is coming down more and more, in the south, and so we probably need to reevaluate this kind of study in a greenhouse in different locations. All right. So teaching greenhouse, right? This is the teaching greenhouse light distribution. This is a sawtooth greenhouse oriented north-south, and then because of the gutter and then also the window panel, I think, having a huge, how do I say? The difference, spatial difference in terms of light intensity. We by the way, we did measure this instead of doing a simulation because it's a little bit high level engineering approach, lots of math. So instead of doing that in a class I was teaching, we put the sensors in the greenhouse, which is a disposable sensor which has dye absorbing sunlight, and the absorbance of that color changes, dissipates. And then, so that you can measure the in the spectral radiometer and then correlate the total energy received by that particular location. So we put, I don't remember, but 30, 40 sensors in that greenhouse, and then measure the light distribution. But you can see that this is a cumulative of 69 hours, big, high radiation area and low radiation area. And then those areas is definitely, it's in here. Okay, sawtooth greenhouse design. Okay, design of the greenhouse does affect. Okay, the roof shape and everything, it affects. And sawtooth greenhouse originally designed for the use in the north, the other way. Designed for the use in east-west orientation. The greenhouse was supposed to be east-west, vertical wall supposed to face the south. So that's the original idea of north-south. And why? If it is the standard greenhouse roof, and then if this is the gutter connected and east-west oriented, the sun is coming through the south-facing wall, and then some of the light is reflected, right? And then making that particular wall more vertical orientation, you can reduce or minimize the reflection, because the incident angle is much, much smaller, right? Closer to perpendicular situation. So that much of the light is coming into the greenhouse. And then reflected one is actually reflected back onto the glazing, and then creating another chance to get absorbed or get into the greenhouse. So that's the original idea. So the sawtooth design was supposed to be used east-west so that light distribution can be more uniform and average transmission is higher. So that was the original idea, whoever I cited in here. In our case, I'm not sure, but most likely because of the wind, probably natural ventilation considered, or something totally different idea, so that's where they put this way, and therefore you see a huge, shadow pattern in that greenhouse. So good example of, greenhouse design critical for maximizing the light transmission. Okay. Sawtooth?
No, what would you say is the best design?
Best design in terms of light transmission. Light transmission. I would select film, okay, and then that having a low thermal transmission, so that keep the temperature higher. The film, because structural component is less, so that more light can come in. And then I want to select a film that can last longer. Rather than standard 3-4 years, I want a film that lasts 20-25 years, which exists. But it's as expensive as glass. So that's my ideal, my best glazing. Yeah, probably round. Yeah, because of the film. But it could be straight, but round is probably easier. Yes, Hailey.
Well, I know that Kenneth and I took Dr. G's greenhouse engineering class last year, and I think that the structure, like the shape, really depends on where you are. Because I remember Dr. G telling us that with the sawtooth, it was originally designed so those vents on the vertical sides could open for ventilation, but it's so dry here that we don't do it because then we lose all the moisture out. So like it really depends on what you're.
Yeah, Hailey is saying that design should be selected based on where you are, what the climate you have. Exactly, yeah, you are correct.
For this climate, what would be the most appropriate structure?
What would be the most appropriate structure? I still pick my idea. Yeah. Structure design, depending on if I'm standalone small grower or the multi-bay large grower.
Like medium grower.
Okay, let me think, and we can discuss more Wednesday. Okay, all right. There are lots of things I can inject, but I want to finish up. So glazing technologies to change light quality, which has been studied many years now. But other than changing diffuse direct radiation, and then also cutting a little bit of near infrared, not so much in terms of actual, the plant responding light quality. But I'm going to go through, okay? There are UV transmitting glazing materials. Some glazing materials are transmitting more and some less, and then plants would respond that. And near-infrared transmission, some materials are very low, so that the thermal property is better. You learn better probably on Wednesday why. And some materials can change the type of radiation. So the incoming radiation may be 80% direct radiation, but transmitted light could be nearly 100% diffuse, right? That could be possible. like this one, diffuse film, clear film. If you can see through clearly, that means that particular film is transmitting direct light and not changing any ratio. If you don't see through, it's like this one, diffuse film, then the light is diffused, right, by that material. But the challenge of this kind of material, most of them are deflecting or absorbing more than clear film. So by selecting diffuse properties, you lose some power, and that's the challenge. But there is a film that has highly transmission of the global total doesn't change, but changing diffuse and direct rate. So that's what we call ETFE material, and that's the only one I know doesn't change the total, but change the ratio. All right, and then there are some studied red far red controlling glazing, enhancing either of the red or far red to do some special, plant response. Okay, and then there is some light converting film. There's a pigment, and that absorb one kind of light and then inject as different kind of the color. That's also available, but still I would say under R&D status rather than commercial. Okay, so under clear film, diffuse film, you can see the difference in terms of shadow. Those two greenhouses are under the ETFE film, so the total light is not different, but the shadows, basically the direct light is largely reduced in a diffuse film condition. And diffuse film is good because diffuse light can penetrate more in the canopy. So if you actually measure the extinction coefficient you learned before the spring break, you should be able to have low extinction coefficient under the greenhouse having more diffuse light property, right? Because the internal canopy can receive more light, so that means coefficient of extinction coefficient should be small. And actually the lot of studies, Asian countries and European countries, they tested diffuse versus non-diffuse glazing. And then many studies prove that, yes, it works, increase the yield, very small percentage, 4%, 7%, so that range, because those countries already have diffuse light, plenty of diffuse light in incident light. So having the very small portion of direct light converted to diffuse light is very small impact, right? So I'm going to show you the table here, which is very important as an arid land, potential greenhouse users or R&D person in the future. So this is comparing diffuse percentage in the 3 locations, including us, Tucson, Arizona, and January to December, and this is the annual average, and then just focus on the diffuse percentage. The Netherlands, 70% diffuse, only 30% direct, and then the study showed that changing 30% of direct light, a little bit more diffuse, so the total diffuse is maybe 80, 90%, and then they got 5% yield increase in cucumber. So that's what many people are reporting from the Netherlands. Tucson, we have only 22% direct light. Oh, sorry, the other way, diffuse light. So 80% or a little bit less than 80% actually coming as direct. So if I convert that direct light to diffuse light, maybe we have more impact. So someday I like to do that side by side comparison. I wish I could do. Anyway, so it's an interesting area. Yes, TJ.
What do we mean by the percent? Out of 100% light entering the greenhouse, 70% or 22% is diffuse?
This is, yes, but this is an incident light, so outside the greenhouse. So the natural light. So natural light, some percent is the direct, which is creating shadow, and then some percent is reflected by the sky. That's the diffuse light. So if you look at the other number, this is a total radiation, megajoule per square meter, and then much lower light energy in the Netherlands compared to Tucson. So the Tucson, Arizona, we have a much higher total radiation and much higher direct light percentage. So the most of the light is coming as direct light. All right, so that means once it hits, it creates shadow and that's it, right? So it doesn't go deeper in the canopy. All right.
So that would be an argument to use like the polypex greenhouses. You could do solid sides and wall, but then cover it with the
Diffuse, that's right, that's right. Yeah, that's right,
more light.
that's right. But that is probably losing a lot more light because of the diffuse property, because it's a PE material. So total transmission is less than clear plastic. Probably, I don't exactly know, but definitely lower. But some material, it's a polymer-based material, wouldn't lose the total energy, but still convert the direct to diffuse. And that's the material that Dutch study is basically using. Because otherwise, it's not comparable. It's basically comparing orange and apple. But you need to have the same light level and then different component of diffuse. All right. Okay. So this is a summary of the light quality relative to the greenhouse glazing. So what is important? UVA, UVC. UVC doesn't exist, so UVA and B in terms of sunlight. And many materials transmission are different in that range. Right? Far red is almost the same, and heat is slightly different. All right, and then this, I think I showed you, glazing impact on the anthocyanin development of the lettuce, same age, same variety, under the polycarbonate, which transmit very little UV. The middle one is the acrylic, which is equivalent to glass, probably 60% transmission of UV. And the left-hand side is the ETFE, which is 80-90% UV transmission. All right, how am I doing? Okay, all right, so this one is just showing my greenhouse transmission relative to the outside. This is outside level, 350 to 840, and showing different greenhouse. And then just by looking at those numbers, raw numbers, measured, at each wavelengths, it is very difficult to see the property. So what you want to do is converting this into the transmission percentage. So this is a transmission percentage of those three greenhouses I showed in the previous slide. So now you can see that my one of them here, the red line, is having a very low UV transmission compared to the other two. And that is definitely affect the plant response. This is my ETFE, which is in fact the strawberry greenhouse used that, having a transmission very nicely from the UV. My sensor can only measure starting from UVA though, UVA all the way to whatever. All right. Okay.